our research on enhancing urban climate observations in high-density city with high spatial and temporal resolution using machine learning. Okay, now let's begin. As we know, the rise of mega and high-density compact urban regions is now a non-reversible trend of urbanization, especially in developing countries. High-density mega-urban living has brought a series of environmental challenges and problems, such as urban heat islands and air pollution. Therefore, characterizing the spatial temporal variability of the near-surface thermal environments at fine resolution is essential to investigating the topic like urban heat, energy consumption, thermal comfort, and heat-related risks. Perspectively, it's become more crucial in the context of climate change. So, an accurate and in-depth understanding of the thermal environment, including air temperature, relative humidity, and net effect temperature, will help to provide scientific, evidence-based finding for policymakers to achieve sustainable development. There are three general rules for mapping thermal environments. The first is interpolation or regression using weather station data. Weather station can provide high temporal resolution and stable observation data, but it's difficult to capture the spatial variation of thermal environments in built-up areas with complex urban morphology. The second route is climate model simulation. It can map the thermal environment with high temporal resolution, but usually with coarse spatial resolution and with high requirements for computing sources. And the third route is regression based on remote sensing data. It can provide a broad spatial coverage, but it's difficult to achieve the high spatial resolution and high temporal resolution simultaneously. And in addition, it usually highly depends on weather conditions. So in this study, we include new significant impact factors, the LCZ, local climate zone. LCZ can allow us to investigate at fine scale intra-urban distribution of thermal environments because it includes 10 urban land types that classified by building morphology, density, and materials. And LCZ has been demonstrated to correlate with urban thermal environments. So in this study, we aim to combine the weather station data, LCZ-based landscape patterns, and machine learning methods to estimate the hourly thermal environment distribution, including air temperature, relative humidity, and the NET. Specifically, we employed a random forest model to estimate the distribution of air temperature and relative humidity respectively, considering the LCZ-based landscape drivers, topography, and the meteorological drivers provided by the weather station. And then we combined air temperature and relative humidity to calculate the NET. We use this framework to estimate the hourly thermal environment distribution in summer seasons from 2008 to 2018 in Hong Kong, a typical high-density city with complex urban morphology at 100-meter resolution. In previous studies, it was challenging to conduct multi-year LCZ mapping due to the limitation of obtaining LCZ sample and classification accuracy. Even the LCZ maps is generated for different years, they lack of temporal consistency. So the innovation of the LCZ dataset used in this study lies in the achieving temporally harmonized LCZ data through a route-based filtering and change detection algorithms. It has a spatial resolution of 100 meter and covers three major urban agglomerations in China, including Beijing, Tianjin, Hebei urban agglomeration, Yangtze River Delta, Guangdong, Hong Kong, Macau, Greater Bay Area. So we extract the LCC data of Hong Kong from it and calculate the landscape drivers. This slide shows the result of our hourly air temperature mapping. The validation result shows that hourly TA maps achieved good accuracy during 2008 to 2018, with mean values of R square was 0.87. The two GIFs shows the average hourly air temperature for the 2018 summer in Hong Kong. We can see that the air temperature distribution estimated by RF model achieved a similar spatial patterns compared with the distribution estimated by Kriging interpolation, but with more spatial details. And the generated hourly TA maps by RF model showed a pattern of slower cooling processes in the urban core area during the nighttime than that in the urban fringe. This slide shows the result of hourly relative humidity mapping. The validation result shows that hourly RH maps also achieve good accuracy, with mean values of R square was 0.88. And we can also see that we can see that unlike the air temperature like before, the spatial heterogeneity of RH distribution is relatively weak. And by analyzing the importances of driving factors, we found that TA and RH are the most critical drivers for each other. But TA has a greater influence on RH than RH has on TA. In addition, landscape drivers contribute less to RH mapping than TA mapping. These two figures shows the spatial pattern differences between air temperature and relative humidity via a zoom-in view. We can see that this spatial distribution of air temperature has a stronger relationship with the landscape and urban morphology than that of relative humidity. In the validation section, we compare the accuracies of our thermal environment mapping to other products that with hourly or daily temporal resolution. Overall, our hourly thermal environment has better spatial and temporal resolution and achieves comparable or even better accuracy. The two figures on the right shows the differences of accuracy of TA and RH in different hours in one day. The mapping accuracy of TA and RH showed a regular circle throughout a day, and the mapping accuracy is higher during nighttime than during daytime. We suppose this may be related to changes in solar radiation and external energy source. We combine the air temperature and relative humidity to calculate the NET. The equation for calculating NET is shown here, and the setting of the constants in the equation was applied in the previous study of Hong Kong and adopted by the Hong Kong Observatory. From the equation, we can see the NET is determined by TA, RH, and wind speed. In this study, we set the wind speed to 0, so we can see the generated NET map is NET distribution under the calm wind condition. The figure on the right shows the spatial differences between NET and TA. The 100-meter hourly assessment reveals that the core urban area cools more slowly at night than the fringes of the urban area. In addition, people in built-up areas face more severe thermal stress at night than the actual air temperature. In addition to the application in a high-density city, we also try to apply the same approach to a larger scale. We conduct hourly air temperature mapping in Guangdong province from 2008 to 2019 for the summer season. The validation shows that hourly air temperature maps of Guangdong also achieve good accuracy with mean values of R squared was 0.8. And the air temperature distribution estimated by the RF model was generally consistent with that estimated by the IDW interpolation, but with finer spatial details. So that's all I would like to share today. And thanks for listening. If you have any questions or want to communicate after the meeting, please feel free to contact me. Thank you.
Thank you very much for Shida from University of Japan. And I have two questions. How did you decide to use random forest model in your machine learning system, not neural network? And second question is this your method can your method to be used to the estimate the radiation environment or in the future climate.
Yes, this study we did not focus on the comparison of different models. So we just find a way to combine the weather station data and the landscape data to achieve a fine scale thermal environment distribution. So your question is quite interesting. I will try to compare different models to achieve maybe a better accuracy. Yeah. The second question you about the use for future.
Radiation. So solar radiation for the long term radiation environment.
The future or future.
For the future climate.
Yeah, in this study, we didn't use the future climate data, but I plan to extend this study to future to cover the maybe more interesting finding about under the future climate scenarios.
Okay.